I'm a radio astronomer, and I work at Metsähovi Radio Observatory, which is the only radio astronomical observatory in Finland, and also a significant research and learning infrastructure of Aalto University. This is our radio telescope, and I'm almost tempted to say it's my telescope, because astronomers often get quite passionate about their instruments, and why not? I mean, big dishes like that, they're quite impressive, and you can do lots of exciting things with them. I'll tell you a bit more about this telescope in a few moments. It can be fairly said that astronomy is the oldest science. Before there was artificial lighting, this is what our ancestors would have seen. Lots and lots of stars and the magnificent Milky Way stretching across the sky. And we also have evidence that even 30,000 years ago, already people started to collect information of the celestial objects. And we know that because they started to make primitive calendars at that time. But the visible light is only one side of the whole story. There's a lot of invisible stuff that we need to use other frequencies to study. And this is an example of how our own Milky Way galaxy looks at different wavelengths. In the optical, which is here, you can see that most of the light of our Milky Way is obscured by dust clouds, and we can't really see, for example, into the center. But if we use other frequencies, going from the really high energy frequencies like gamma rays and X-rays on the bottom, or the longer wavelengths at the top, like radio frequencies, we can tell a lot more what's going on in our own galaxy. And each of these frequencies tells a slightly different story of our galaxy. And we need to study all of those so that we know what is really going on there. And radio astronomy was the second one after the optical astronomy to be developed. And this image here tells you why that is. Because there are two windows that we can see through in the atmosphere. The first one is the optical window. Of course, we can see the stars and everything there out in space. And the other one is the radio window. Everything else, all of the other emissions, especially at the high frequencies, they are stopped by the atmosphere, which is good, especially at the higher frequencies. But if you want to observe them, you need to send an instrument to space to observe it. So it's natural that first we used optical astronomy, and then we developed radio astronomy that we can also do from the ground. It's a lot easier and lots more cost-effective than sending stuff into space. So this is our observatory. You can see a little animation here showing how our telescope works. It's located at Kirkkonummi. The diameter is 14 meters. The main frequencies that we use are 22 and 37 gigahertz. And the main targets are active galactic nuclei, or AGN. I will tell more about those in a few moments. And our own sun. We use different kinds of observing methods. We use the single dish, our own telescope as it is. But we also do what is called very long baseline interferometry, where we combine different telescopes from around the world to simulate a virtual telescope of the size of the Earth. My other significant tool is the Planck satellite. It's located in L2, slightly further away than Kirkkonummi. And it was launched in 2009. I was already involved in this project since 1997, which illustrates the really long time frame it takes to send something large into space. And what was significant about the Planck satellite was the large frequency range that it used, from 30 to 857 gigahertz. And that made it quite significant for my studies as well. The main target of the Planck satellite was the cosmic microwave background, but of course, as that is the furthest thing that you can see in the universe, it also observed everything else in front of that. For example, like you see in this first all-sky survey that Planck made, this is a quasar. It's a kind of an active galaxy that I study. So this was a very handy tool for observing everything in the universe. So what kind of sources are these active galactic nuclei that we study? Here's a little animation that tells you more about them. So active galaxies are galaxies that display some sort of unusual activity. And that unusual activity is because of the supermassive black hole in the very center of the galaxy that you can see here in the center, and an accretion disk of material that is circling around the black hole. And there's also a strong magnetic field. And then something happens, and these plasma jets that you can see in this animation as well are shooting out from the central parts of the AGN core. And you can also see shocks that move in that jet. And this is what we study. So there are different kinds of AGN types, and for the purpose of today's talk, I'm going to mention only two, but there are dozens of different kinds of types. We have what are called radio loud AGN and radio quiet AGN. The radio loud AGN are the kind of AGN that have these radio jets that you saw in the previous image. It's synchrotron emission, so we see them at radio frequencies. The jets move at relativistic speeds, which means speeds at close to the speed of light. They usually also have high black hole masses, very, very massive black holes. And here you have an image of a typical AGN, the kind that you see in the animation on the previous slide. These are the radio jets here, and this is the optical galaxy in the middle. This is what you would see by eye. It's actually an elliptical galaxy, as most of the radio loud AGN are elliptical galaxies that are kind of an older type of a galaxy. In contrast, the radio quiet AGN, they have either no radio jets at all, or they are very weak, more like outflows and not necessarily relativistic powerful jets. So when you're looking at a radio quiet AGN, you would most probably see just the optical galaxy in the middle and nothing of this stuff here. And they usually have much lower black hole masses. And they are hosted by spiral galaxies that are younger. So there's a clear division here between the radio loud and the radio quiet. The other ones are powerful, massive black holes, elliptical galaxies, old. And the other ones are low black hole masses, no big radio jets, and in young spiral galaxies. At least this is what we thought a few years ago. Actually, this picture is now changing based on a lot of the investigations that we have done at Metsähovi. So let's first look at the radio loud AGN, the really powerful sources with the massive relativistic radio jets. This is what Metsähovi has been mostly doing. On the left, you see a light curve of observations at 37 gigahertz from Metsähovi, time on the horizontal axis, and on the vertical axis, you have the brightness of the source. The brightness is described by a unit called Jansky, in honor of Carl Jansky, one of the pioneers of radio astronomy. And basically, 1 Jansky is 10 to the minus 26 watts per square meter per hertz. So that means it's a very, very, very small number. And actually, radio interference is becoming quite a big problem for our observations because, as an example, if you take a normal mobile phone and you take it to the moon, it would be the brightest thing in the sky that our telescope sees. So you can imagine what a mobile phone does at a closer range. So this source here, 3C4.3, is one of the really strong AGN that we observe, and we've been observing it since the early 1980s. Now we need to combine this information with the other frequencies, as we have seen earlier. So what we do is that we gather simultaneous observations of the same source also at other frequencies. And here's an example of a spectral energy distribution of this source, so that we have all the frequencies from the radio all the way to the gamma rays up there. And in this particular SED, you can see the Planck and Metsähovi data at this point there. Then we have the optical X-rays and gamma rays. And we can do quite a lot of science with this sort of light curves and spectral energy distributions. So what do we do with it, actually? We have to insert it into theoretical models. We have collaborators, for example, at Boston University that make these kind of models of quasars or AGN. And they take our data and they try to figure out how that transfers into a nice model that describes what is going on in these sources. From the supermassive black hole that we have in the center, Then we have the accretion disk and the magnetic field, and then something happens and we get the plasma jets out of somewhere in the vicinity of the black hole. So this is what we try to do. We give the theoreticians the observations that they need for developing their models. So this is what we can easily do with the radio loud objects. So what about the radio quiet ones? We also wanted to take a look at those. What we can find. I mean, if you have a radio telescope and you are a radio astronomer, what do? You take something that you're not supposed to see and try to see it anyway, because that is interesting. And that's what we did. I started a project in 2012 to observe a set of radio quiet and radio silent AGN called narrow-line Seyfert 1 galaxies. It's a very particular kind of a galaxy. They are supposed to be young in the very first stages of their development. And if they have jets, that would be very interesting to see how that sort of impacts the whole evolution of the galaxy. So we started to observe a set of these sources. We have about 250 in our observing list at the moment, and this is what we got. I mean, this looks a bit boring. It's just like fly poop on a wall, but each of these is a very significant observation of a source that have been never before observed at these frequencies. What you can see here, this is the same flux density that we have in the previous images. Now we're talking about less than Jansky values. In the other one, the strong source was about 30 Janskys. So this is even fainter than that. And we managed to detect this at 37 gigahertz at Metsähovi. And if we observe something at such high radio frequencies, it automatically means that the source must have a relativistic jet, a jet that is propagating at the speed of light. And this means that we are not talking about weak outflows of young sources, but we are talking about fully developed relativistic jets. And that makes a big difference, because these are the young sources in spiral galaxies, and they are not supposed to do this. Well, then we moved on to the completely radio-silent AGN. These are the kind of sources that have been observed before, or people have tried to observe them before at lower frequencies. But the image fields at lower frequencies are completely empty, which means that like 20 years ago, there was nothing there in the spot where this galaxy lies. But then what happened was that we observed this source at Metsähovi, and we detected it. And it was even stronger than the one that we just saw up to 1 Jansky level. And what was even more interesting was that we also detected at gamma rays the same source. And radio emission and gamma rays, they are both generated in the relativistic jet, which means that now we have two pieces of evidence that tell us that these kind of sources can have powerful relativistic jets. And this was quite unprecedented. This is something that we did for the first time at Metsähovi. So we need to start thinking about this problem in a different way. Because in the old world, we had these two kinds of sources. We have radio loud AGN and the radio quiet or silent AGN, of which the narrow-line Seyfert 1 galaxies are one example. And if we look at their properties, here they are listed. They both have relativistic jets, but their black hole masses are significantly different. For the radio loud AGN, it's more than 10 to 8 solar masses. For the radio quiet ones, it's less than that, sometimes 10 to 6 solar masses, which is quite featherweight, if you can say that about supermassive black holes. The host galaxies are completely different. Old ellipticals compared to young spiral galaxies. And the large-scale environments, meaning the cosmic environments where these sources live, are different as well. The radial loudness tends to be connected to superclusters and very dense environments, whereas the radio quiet and silent sources seem to live in voids or intermediate density regions. But the one thing is, what's important here is that despite all these differences, one thing is common: they both have relativistic jets. And this was unexpected. We also need to change our way of saying radio loud and radio quiet, because obviously this doesn't hold anymore because we have jets in both. So what we're studying at the moment, the first question is, what triggers the relativistic jets in AGN? Well, we know that it can't be the black hole mass because they are really different in these different kinds of sources, but it could be the black hole spin because, as you know, black holes have no hair, which means that the only properties that they really have that are measurable are the mass and the electric charge and the spin. And this is one possibility because spin affects the magnetic fields in the centers of the galaxies. Also, the large-scale environment, the cosmic environment, may play a role, or the interaction between galaxies or mergers. And we know that this kind of activity is happening because in this picture there, you can see two galaxies merging, one of the sources that we have measured. This is an optical image taken with the Nordic Optical Telescope. And when we have hopefully solved this problem, we want to look at the evolutionary sequences between source classes. How do these sort of baby jets in young spiral galaxies grow into these massive, big, relativistic, powerful jets? So what's in store in the future for radio astronomy? Well, starting from the most important bits, for me at least, we are planning to acquire a new receiver at Metsähovi, which would mean improved sensitivity and significantly lower detection limits. And also we could get polarization observations. That would give us a lot more sources that we can observe at much lower detection limits. We're also building an array called Metsähovi Compact Array, which is going to be the first interferometer in Nordic countries. You can see it over there. It consists of 3 or 4 or 5 meter telescopes, and this will be designed and built mostly as student projects. And then something quite remarkable globally is the Event Horizon Telescope, which is an array of radio telescopes all around the world that uses the very long baseline interferometry technique to try to take the first radio image of a black hole shadow. And the target for this one is the supermassive black hole in the center of our own galaxy. So hoping to get this image very soon, in the next couple of years, possibly. And of course, if a virtual telescope the size of the Earth is not enough, you can always send a telescope on orbit, and then you get a virtual telescope the size of that orbit. And with Space VLBI, we can actually get the best resolution available at the moment in astronomical observations. And radio astronomy is a very, very versatile tool with very wide frequency range. You can observe sources in our own solar system, like the sun. You can see through the dust clouds in our own Milky Way, and you can see the furthest thing in the universe, the cosmic microwave background, and everything in between, like the AGN, that were the topic of this talk. So radio astronomy is the perfect tool for learning how the universe works. Thank you.